Good afternoon, folks. Good afternoon, good afternoon. All right, hold on, bear with me. We're just gonna get some people in. All right, good afternoon. All right, folks. Just gonna give it a couple more minutes. Being that this is our first lecture and I wanna make sure that everybody has the time that they need to get in. If anybody's struggling to find the link, I figure we'll just take a couple of moments here to just relax for a second, take a deep breath. It's been a long day. Please do me a favor and just make sure that your name on Zoom matches your full first and last name. Strictly for attendance purposes, I want to make sure that I have all the names that I'm supposed to have. And also I want to make sure that, excuse me, I want to make sure that I'm not just letting random people into class. You can't hear me, Alex? Can everybody hear me, or is it just Alex that's struggling to hear me?
I can hear you.
All righty, thank you, Audrey.
I hear you well as well.
All right, thank you, thank you. Alex, I guess let me type in the chat. That's really funny. And forgive me if I'm saying your name wrong. Barrier, your icon on Zoom is just showing up. It's like a tiny little speck on my screen. I swear I thought I had dirt and I'm just sitting here for like 2 minutes trying to scratch it off. That's really funny. Oops. It's okay, no worries. No problem. All right. All right. So, folks, a couple of things. Oh, there we go. See, I knew people were going to be showing up a little late. Okay. So, two things to start with. And I'm sure I'll be saying this more as people join class. When you join, make sure that your name on Zoom matches your name as it would show up on the attendance roster. Right, that way, when I see that you're in the waiting room, I can make sure that I'm letting in people that are actually supposed to be in this class and not, you know, a friend that got a link or something rather. Okay, the other thing that I'd like to ask you all to do is to include your pronouns in your name on Zoom. Just, you know, whether you are binary or non-binary, I want to make sure that I'm using the right pronouns when I'm speaking with you. And I want to make sure that your classmates are also using the right pronouns. So whether you're binary or not, please go ahead and add to the end of your name. I think if you click on the 3 dots on your picture, hold on, give me 1 second. If you click on the 3 dots in the picture, you can add that information. All right, give me 1 second. Okay, great. Yeah, please, folks. It looks like a lot of you are still missing your pronouns at the end of your name on Zoom. Thank you, Ed, for making the change. All right, is anybody struggling to do that? All right, and it's important that we all do it so that we normalize it for, you know, we normalize non-binary pronouns as well. Okay, if you want to go ahead and do that, you go ahead and you hover your mouse over your own picture, or you can go into the participants list and find your name. There should be a little option that says more. All right, when you hover your mouse over your name, you can click on that and it should say rename. Thank you very much, folks. I greatly appreciate you doing this for me and for each other. Thank you. And this is just going to be, this should just be the norm that we come in and do this. Because, well, it's just more inclusive that way. And we've got some more people. Okay. All right. Seems like everybody sort of found their way in to class tonight, which is great. If you wouldn't mind, this is not something I'm going to ask you to do every day. Rarely ever, but if you wouldn't mind, being that it's the first class, just turning your videos on so I can see what you guys look like, know who my students are. Hello, Zach. Zach, you look so reluctant to turn your camera on, but I appreciate you doing it, man. Thank you very much. Angeli Sani, am I saying your name correctly? Okay, thank you, Sani. All right. Alexa's turning the camera around. Hi, Alexa. And Deanna. Oh, not you, Alexa. Damn technology. Miss Rodriguez, that must get so annoying. Alexa, stop. I might have to unplug it, I swear. All right, Sewang, am I saying your name properly?
Hi, Professor. How are you?
Hi. Did I say your name correctly?
Yeah. So,
wonderful. Wonderful, wonderful. And Deanna, good to see you. Chris, okay, it looks like you got the lights off over there. All right, so for those of you that just joined, please make sure that you go ahead and you change your name on Zoom so that it includes your pronouns. Right? He, him, his, she, her, hers, they, their, them, so on and so forth. All right. Please go ahead and do that. It's important that everybody has it. Okay. All right. So let me just start by asking a couple of questions here. Is everybody that's here right now enrolled in the 2633 section of Scp140? Right, we're all part of the Monday afternoon. Okay, wonderful. Do you have any questions about the syllabus? I imagine that if you are here, you either saw the syllabus or Audrey, I just wanted to see if, see everybody's face for the first day. And then if you don't want to keep it on, you could turn it off. It's up to you. I just want to know what you guys look like. All right. I'm sorry, where was I? Hi, Audrey. Thank you for getting the camera. You look like you're somewhere exciting. That's not home, because if you were home, I can't imagine you'd want to be wearing your mask right now. Okay. So folks, where was I? Were there any questions about how the weekly schedule works for this class? I tried to make it as concise as possible because in the fall, the students that I had struggled. Also, I mean, it was the first time that many of them were using Zoom and taking an online class, but just because I'm teaching 2 sections of the same course, I'm going to record half the lecture during our session. I'm going to record the other half of the lecture during the other class's session. And then it's your responsibility to watch that lecture sometime before next Monday, right? Which really means that instead of us meeting on a Monday for a 3.5 hour or 3 hour block of time, we're only going to be meeting for about an hour and a half. So maybe that makes your day a little bit better. I don't know. Okay. So let me start by introducing myself. And let me get my slide going here so I can do my share screen. Okay. Here we go. It is so much better starting this semester on Zoom and not on Blackboard Collaborate, because Blackboard Collaborate is the absolute worst. All right. It's just, barrier. We're always going to be starting at 3:45. It's going to be better, or personally, it's going to be better because I am a high school teacher during the school day, which I'll get to in a second. And I won't be home until, just if there's traffic, I don't want to cause anybody to be sitting here waiting for me. I'd rather just say we're going to meet at 3:45. All right, that was a good question. Okay. So, my name is David Stern. You can call me Professor. You can call me David. You can call me Professor Stern. Whatever you're more comfortable with, I will respond to all of the above. But if you start to get fancy with it and try calling me like D-Dog or Stern Man or something like that, I might not respond to you. All right. I am a high school teacher during the day, and on summer breaks and during evenings, I lecture at LaGuardia. I've lectured topics in astronomy. I've lectured an introductory physics course, and I've been with LaGuardia for several years. But I am a physics teacher by trade. I also teach astronomy and earth science to high school students right here in New York City, in Queens. I teach over at Townsend Harris High School, so I commute from Long Island City to Queens College every day. It's nice to be driving against the traffic, which is pretty fun, but that's pretty much me. And I'll answer any other questions that you have if you ever have any. But that being said, if you ever want to reach out to me, my email address is dstern@lagcc.cuny.edu. I don't know about you guys, but I've always found that I have so much spam in my LaGuardia email account every single day, just from like faculty that's like blast spam to every other faculty member. It's the worst. So if you want to send me an email with something regarding class, just make sure that you put Scp140 like first thing in the subject line. That way it'll catch my attention. There will be office hours each week. The office hours will be on Tuesday evenings from 7 p.m. to 9 p.m. I think the first couple of Tuesdays, I'll leave it open just for people to drop in and see, sort of whether or not you guys feel like it's important to show up, or if you have any questions. And if not, then maybe I'll switch it to by appointment only, right? And then you just let me know when you want to meet, and I'll make sure that I'm available on that given Tuesday. Okay, so a couple of important points. This course is graded based on 4 main things, right? Your grade in this class is going to depend on 4 things. One is your involvement in weekly discussion questions. That's going to be worth 25%. In fact, each of the 4 things is 25% each. So 25% for the discussion posts. The discussion posts are going to be made available every Monday morning at 8 a.m. So if you logged in at some point today, you probably saw the first discussion post. And it's going to be graded on a 5-point rubric. 3 of the points are for content. So are you answering the discussion prompt with, scientific language? Are you including concepts that we're discussing in class? Are you making sense? And things to that effect. You can always check the rubric. And the other 2 points are going to be for responding to classmates in their own threads. So that's also going to be an important part of this course, is that you keep the conversation going, right? A lot of the learning that we do is going to be through those discussion boards as well as through lecture. This is the first semester that I'm ever doing a discussion board, or that I'm implementing discussions to such a high degree of your grade. Traditionally, we would give 3 quizzes, which are effectively 2 midterms and a final. And we're not doing that. So you guys don't have any tests or quizzes this semester. Yay, I know you're also happy about that. All right, so that being said, you are responsible every week for participating in this online discussion. Speak in full sentences, explain your thinking. Don't just say, I agree or I disagree. Thoughtfully comment on what people say. I think it's important that if you're going to cite certain things or share things that you've read on the internet, that you attach a link to those websites so your classmates can go in and see where you're getting your information from, and they can do more exploring and research, because in the end, that's what all this is about. Everybody here, I imagine, knows how to use the emojis. Not, I guess the emojis, geez, what are they called? Reactions on Zoom. Everybody here is familiar with reactions. Just use the little wave just so that I know that you know where to go to have a reaction during class. Or you can just actually have your camera on and wave. Thank you, Alexa. And Sani, thank you very much. Okay. Okay. So I see Tiffany's got it. Everybody else? Deanna, Audrey, thank you for the camera on. Very nice. Ed, Gabriel, okay. So barrier, how do you do that? On the bottom of your screen where you have like the options for mute and stop video. Great, awesome. Great, and you can do that, and I think somewhere maybe in the participants list, or somewhere you have the ability to put like yes or no reactions or something like that. Okay. By a show of hands, how many of you actually want to go into astronomy as a career? Exactly as I thought. Okay. So being that we're all not trying to become hardcore scientists here, hardcore astronomers, right? Whether you're taking this class because you need a lab, credit or, whatever it is. Maybe you thought this was astrology and not astronomy. There is a difference. We'll talk about it. It is, the purpose of this is to learn, right? Whether or not we're actually going to make a career out of this content, we want to learn about astronomy while we're here together. And so that's what we're going to do. Okay, so moving on. What is astronomy? Does anybody think that they can answer that? You guys are going to get used to this really fast. I'm very interactive. I'm not just going to sit here and lecture at you for an hour and a half. I'm going to speak with you, have discussion. Zach, I see your hands up.
It's study of the stars, the planets, and galaxies, if I'm not mistaken.
Stars, planets, galaxies. Awesome, Zach. Can anybody else add anything to that? What else are we going to talk about in astronomy? Stars, galaxies, planets.
The life of a star and the different stages that I'm assuming goes through.
Yeah, stages of a star's life. Absolutely. Stellar evolution is what we're going to call it. Tiffany, what else do we got?
I think you wrote about the Milky Way or something. I don't know.
Yeah, we're going to talk about the Milky Way. We'll talk about, that's going to be part of our conversation on galaxies. Anybody else? Anything else that we can add? Barrier, you got something for us?
The study of space and the expansion of how everything and why it works.
Yes, the study of space, right? And expansion of that space.
Yes.
This place that we're living in, AKA the universe, right? So we're going to study the universe as part of this course. And there's so much more to it than that, right? We're going to talk about, well, here's technically the definition of astronomy, but on the next slide, I'm going to show you just, the breakdown of what we're going to talk about in this class. And Zach, just letting you know, the hand is still up. I don't know if that's to add something or if that's from before. Just calling it out for you. Yep, got it. Okay. Let's see. Okay, so what is astronomy? All right, we're going to talk about moons, planets, stars, nebulas, galaxies, and then there's so much more. We're going to talk about the day and the night sky. Right, we'll talk about the seasons, why we have them, where else in the universe are there seasons. We're going to talk about the Copernican revolution, which is going to include one of the most dramatic shifts in scientific thought in human history, right? But we're also going to talk about a historical astronomy in terms of ancient Greek, their view of the universe and how their developments shaped our understanding of the world that we live in. We're going to spend a lot of time talking about starlight. Without me saying much more on that, it is incredibly important. We're going to talk about properties of stars and planets, right? How are the stars different from each other? Why are the stars different from each other? How are the planets different from each other? Why are they different from each other? All right, we'll talk about how a solar system forms, like the one in which we live. We'll talk about black holes. Right, in the past couple of years, since 2016, there's been a lot of exciting stuff happening around black holes, around the topic of black holes. There's always exciting stuff happening around black holes, but around the topic of black holes also. And we'll talk about galaxies, and that will lead us into modern cosmology. Right, and so there's a lot to talk about in this class. It's not, there's a lot of depth to all these things, and we're gonna stay, fairly surface level with a lot of it. We're gonna cover a broad range of things and not go too in depth on any given topic. There's always more in depth to go. But I want to start now, now that we've addressed some of the things that we're going to talk about in this class. Forgot about my pictures here. We got opportunity, the opportunity rover. Got a shooting star. Got a nebula there. Some fun pictures. Astronomy pictures are always so cool. They're just like beautiful to look at. Okay, moving on. So we're going to talk about the nature of science, right? Which is effectively, thinking about how do we involve ourselves in the scientific process? How does one do science? Right, how does one do science? What does that mean to do science? Do you do science? I don't know. Do I do science? Perhaps. All right, so what do you think that means? What is the act of doing science? Barrier?
Conducting experiments and predicting hypotheses and like what will be the outcome to your experiment and stuff like that.
Can anybody else add anything to that? That was a good start, Barrier. Anything to add? That was the best start I could have hoped for. But there's more to it, right? It's not just, making the hypothesis and doing the experiment, right? This is a cyclical process, right? Doing science doesn't have a starting point and an ending point. And I think that's a really important thing to wrap our heads around, right? That science, just learning about one thing leads into the next thing, leads into the next thing, leads into the next thing. All right, so it starts with asking a question, right? You say, I wonder why this acts this way, or I wonder why this is like this. I wonder what would happen if we did this to something, right? And we just sort of ask these silly questions that, for whatever reason, adults are really bad at coming up with. Like, kids are the best at this, right? Kids ask like the most crazy questions because they don't understand how the world works, and they are trying desperately to figure it out by making connections to things. All right, so a kid might say, why does smelling pepper make me sneeze? That does smelling other things make me sneeze? Is it just pepper? What is it about pepper that makes me sneeze? Do peppers make dogs sneeze? Does pepper make a cat sneeze? These are silly questions, but like, that's amazing. That's an amazing scientific question, right? So once you ask the question, then you make a hypothesis, right? Just like Barrier said, you make a hypothesis, you predict what you think is going to happen, and you try to come up with some sort of reasoning for why you think that, right? So, to say, I think the sky is blue because, and then whatever your reason is, right? You have to make sure that you include the reason. All right, and then you devise and you perform an experiment, right? So you figure out what sort of lab equipment you might need, how much time the experiment's going to take. You write out your procedure. You try to make it as clear and concise as possible so that while you're actually doing the experiment, you don't accidentally skip something or do too much or too little of something. It's basically like following a recipe for cooking, right? You want to make sure that you have the recipe out before you bake the food, otherwise you might make it incorrectly. All right, and then once you've done the experiment and you've collected the data, you want to analyze that data, right? You want to look at it and you want to maybe plot some graphs to maybe gain some deeper insights that aren't super obvious when you just look at a data table, right? So like converting something into a graph form is useful. And then asking yourself, do the results of my experiment actually support the hypothesis that I made at the beginning of this? Or do they negate my hypothesis? right? So once you analyze this, you can draw that conclusion, right? And your conclusion has to be grounded in evidence. That's what makes it good science, right? That you don't just you don't cherry pick pieces of the evidence that you like so that it makes your hypothesis work. That's bad science, right? You want to make sure that when you're doing science, you are humble. I think humble is the best word, right? So that whether your hypothesis was correct or incorrect, you walk away learning something, right? That you were either right or wrong. And with that, you can go learn more stuff, right? Now, you want to make sure that when you're going through this process, that you're picking or you're making a prediction that's actually testable, right? You want to make sure that it's something that you can actually conduct, you know, to say like, I'm gonna ask a question and I'm gonna try to do an experiment. I wonder what would happen to my hand if I decreased its temperature to absolute 0. Now, is that prediction testable? I want to say no, because I doubt anybody's going to offer their hand up to being frozen. Like absolute 0 means that you've lost a hand. You don't get that hand back after you bring it to absolute 0. 2 is you don't really get any, we don't have the technology to bring the temperature of something to absolute 0. So you can't really test that. You know, that's not a question that's testable. And you have to ask yourself, are there any biases, right? Are you only seeing the data that you want to see? Or are you sort of above that and you're able to say, you know what, this isn't what I thought it was. This isn't what I was hoping for, but I learned something. And with this, I now know more about the world around me, right? So I want you to think, what are some examples of good science? And essentially what we've just done is outlined the scientific method, right? The scientific method is ask a question, do your research, make the hypothesis, test that experiment out, or test the experiment, analyze the data from the experiment, draw a conclusion. Does it align with your hypothesis or not? And then you communicate that to other scientists. And like I said, it's not, there's no start and finish. I know that this looks kind of linear, but after communicate results, then you would have other scientists verifying it, right? They're going to repeat this test. They're going to do different variations of the test. They're going to use this information to test other things. So it's, you know, it's constantly building our collective knowledge base. Okay, let's move on. All right, so astronomy is a little bit different than your other sciences. How many of you remember being in high school and sitting in your science class lab and getting hands-on with an experiment? You know, maybe you're like seeing what happens when you put certain powders into a flame, right? You see how it changes the color of the flame. Or maybe you are, I don't know, dropping objects off the side of the table and you're measuring the acceleration due to gravity or something like that. And these are all very hands-on examples of science where, you know, this is like a traditional, it's a little bit more of a traditional way of doing things. Astronomy doesn't quite fit in that box because, you know, you can say, I wonder what would happen. I think that we should test the acceleration of this cell phone down this binder. And I think that we should see what happens as we change the angle of the binder, right? And now that kind of experiment gives you a lot of control. We call it a controlled experiment because you get to change the variable, you get to change one variable and see how it affects another. With astronomy, that's not possible because a lot of the questions, most of the questions that we ask have to do with things that we can't touch. We don't have physical access to them, right? So you can't say, I wonder how this this planet's atmosphere would behave if we changed the temperature of the star that it's orbiting. Because there's no dial on Earth that controls the temperature of stars millions and billions and trillions of miles away, right? So this science is unique in that it is almost entirely observational, right? It's a lot of just looking at things that are happening and making inferences about those observations, right? So in this class, we're going to talk about things that are on vastly large and small scales. And I think it's important to sort of set yourself up for this kind of thinking that when we talk about the universe and everything in it, we talk about things on two different things within each of them on a range of scales. So we talk about the universe spatially, right? Like what's where, how things, where things are relative to each other. And then we also talk about things temporally, which means in time. Okay, so we talk about things spatially, which is position-based, and then we talk about things temporally, which is time-based. So like, the temporal scale of a human life, I don't know, somewhere between, on average, what's the average human lifespan? 80 years, right? Whereas the temporal scale on which a star lives is billions of years, right? So we talk about very vastly different temporal scales, things that happen within the fraction of a second, to things that happen over the entire age of the universe that are still ongoing. And then spatially, we also talk about things on a very small scale and a very large scale, right? Because on one hand, we have like these super massive objects in the universe. We have planets and stars. And I mean, like, all our lives, we've been on a planet. We experienced planet Earth, but I'm telling you, there's no way for you to picture just how big and how much stuff our planet is made of. It's just very difficult to fathom that compared to the objects that we interact with on the day-to-day, right? But these immensely large objects are made of atoms, which are immensely small objects, right? So to really understand the universe and how complex it is and all the amazing things there are to learn about it, we have to be prepared to talk about things on small and large scales. Now, math is the language through which we communicate a lot of science. That being said, we're not doing a tremendous amount of math in this class. I promise you that. I'm not trying to make anybody think that they signed up for a math course unknowingly. But we are going to play with numbers a little bit, and it's important to be comfortable reading and writing scientific notation, right? And as indicated on the PowerPoint, this is a tool that we use to express numbers that are very small and also numbers that are very large without taking up like the entire width of our page writing a single number. Okay, so like instead of writing 0.00000000001, you could just write that as 10 to the negative 9th power. Or this number, right, which is 1/1,000,000th, right? This is 0.000001 or 10 to the negative 6. Now, if you look and you count how many times you'd have to move the decimal place over until it's behind that first non-zero number, you're going to find that the number you count to matches the number that's that this 10 is raised to. Right, so for example, 10 to the negative 9, watch this. We'd have to move the decimal place over 1, 2, 3, 4, 5, 6, 7, 8, 9 times. 10 to the negative 9, right? Negative because it's less than 1, right? 10 to the positive 9, which we'll get to in a second, would mean that you're moving it the other way. Right, so typically when we will do two things. One is we will write numbers in scientific notation, and we're also going to write these numbers using prefixes. So for example, 1,000 meters. 1,000 meters, right? That's less than a mile, right? But 1,000 meters, you could write as 10 to the third power meters. If you look on the table here on the right, if the exponent is 3, so if we're talking about 10 to the third, we could just replace 10 to the third with kilo. So 1,000 meters, or 10 to the 3 meters, is 1 kilometer. For those of you who are, really into either building their own PCs or are just particularly tech aware, when we talk about file sizes on a computer, sometimes we'll talk about like really small text files, which are like measured in bytes or kilobytes. And then we'll talk about maybe an audio file that's measured in megabytes. And then you have really large files, like maybe you're downloading an entire trilogy of Star Wars, or you're downloading a game and all of its expansions on your computer, and it's measured in gigabytes, right? Or maybe you just need that extra hard drive because you do a lot of visual computer work, and you have a terabyte hard drive, right? These are the prefixes that we're talking about, and each one of them is some power of 10 different than the others, right? And so that's we're going to practice that in just a moment. All right, let's see here. All right, so Jeff Bezos, all right, richest human on earth. Last I checked, has a net worth of 183.8 billion US dollars. All right, let's take a moment and let's write that out in standard notation. Standard notation means like you're writing the full number, no powers of 10, like you're literally just writing every digit, and then you put the decimal point there after the dollar amount. All right, I'm gonna get my writing pad out over here. And I'm gonna stop this screen share. I'll start another one. Okay, give me 1 second. This always takes a moment. All right, can you guys see this screen? No, it's all black. Hold on. Oh, not that. Here you go. Can you guys see this? Amazing. Okay, so Jeff Bezos, net worth, 183.8 billion US dollars, right? We want to write that in standard notation. So how do we do that? Well, we're going to write 183. And we're going to put a comma there, put the 8 after, and then we're just going to start adding zeros until this gets us into the billions, right? So right now, oh, hold on, let me backtrack for a second. It's probably easier to just start here. So if we write it like this, 183,800, that's 183,800. If we add 3 more zeros and make it 1,000 times larger, now we're talking about $183,800,000. And if we add another 3 zeros, that makes it another 1,000 times bigger. This is $183,800,000. All right, so we've just written it out in scientific notation. Or excuse me, standard notation. Standard notation, okay? That's a crap ton of money, people. All right, just remember, you're closer to being a millionaire than Jeff Bezos is. All right, if you're ever sad, you just think of that fun fact. Okay, now we want to put that in scientific notation. Scientific notation. All right, to do this, we're going to count how many times we have to move this decimal place over from standard notation so that the decimal comes after the first non-zero number. So essentially, we want to move the decimal place so that it's between the 1 and the 8. That's what it means to be in scientific notation, right? We're basically going to turn this into a number that looks like it's between 0 and 9.9. Okay? Excuse me, between 1 and 9.9. We have to move the decimal place over 1, 2, 3. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. So we're going to rewrite this as 1.83 times 10 to the 11th power US dollars, right? Now, if you're not sure whether that 11 should be positive or negative, think about it like this. We're taking 1.83 and multiplying it by this number. All right, are we trying to make the 1.83 bigger or are we trying to make the 1.83 smaller? Ultimately, this is supposed to be a really big number, right? We need to be making the 1.83 bigger. So we got to multiply it by something that's very large. This is a very large number. 10 to the 11 is 100 billion. So 1.83 times 100 billion. 10 to the negative 11 would be this number. Right, and we're not trying to multiply 1.83 times that small number because that would mean that Jeff Bezos is worth nothing. All right, Barrier, what is your question? Oh, I'm sorry, folks. I also, on a side note, I didn't realize that there's so much going on in the chat because it doesn't like ding or anything. And it's just, I have so many different screens up between the PowerPoint and my iPad screen and seeing you guys that I missed it. So I would appreciate it if you just turned your mic on and just spoke out loud. I think that just from the get-go, let's make this a community where we speak and use our voices and not like message each other through the chat. All right, Barrier.
Oh, sorry. What about the last 8?
The last 8, oh, excuse me. I'm sorry, you're right, I left that out. It's still there. It's 1.838.
Oh, okay. So yeah, that was just confusing. Okay, got it.
Yeah, I'm sorry. I didn't mean to leave that out. That was my apologies. All right, so that's pretty much scientific notation in a nutshell. And there will be some opportunities to practice that. I mean, we could try right now, you know, if we wanted to take this number, you know, $12,000 meters, right? 12,000 meters. That's a long ways to walk, right? That's like what? I don't remember how many miles that is. That's a lot of miles, okay? But if you're walking 12,000 meters, how would we write that in scientific notation? Well, again, we'd have to first start by saying, where's the decimal place? Decimal place always comes after the ones place. So the decimal's there, even though it wasn't written, right? We have to move the decimal place over 1, 2, 3, 4 times for it to come after the first non-zero number. So we have 1.2 times 10. Now, is this +4 or -4? What do you guys think?
Positive.
Positive.
This is +4 because we want to multiply 1.2 by a big number to get it back to being 12,000 if we were to convert it the other way. 1.2 times 10 to the 4 meters. And then you can start to play around with it. Well, you know, what if instead of moving it over 4 times, what if we didn't put it in scientific notation? What if we moved it over 3 times? 1, 2, 3. So now we have 12 times 10 to the 3 meters. Well, hold on a second. You guys are gonna have to look back in your notes from the previous slide, right? 10 to the 3 meters, 10 to the 3, that's a kilo. That's the metric prefix for kilo. So this is equivalent to 12, and then I'm going to replace 10 to the 3 with the prefix kilo meters. All right, and that's a little bit of how we play around with that. Okay, let me get back to the slides here because I want to get some stuff done. I'm going to try to keep this class to an hour, maybe a little bit more than that. And then I think going forward, just so you know what to expect, we'll spend like an hour to an hour and 10 minutes or so, I imagine, on content. And then the next like 20 to 30 minutes, I'll be around to help you. If you have any homework or lab questions that you're like trying to figure out, you're stuck on something, or you want to just work on it with people, I'll leave the room open. Otherwise, you are free to go once I'm done talking through content, okay? Unless you want to stick around. Yes, Barrier.
Is there any way for me to access the slide someone on Blackboard?
I will post. Well, I'm going to be posting the recording of this lecture onto Blackboard.
Okay, no, because I thought you said to go back to our slide, so I thought we could find it somewhere. That's all.
I was sorry. That was me just assuming that it was written down because I had it up. But that's fine. If you weren't writing it down, it's yeah.
Right.
Write down the things that you think are most important. Okay. I'm not telling you to write down every single thing that's on my slides, right? But I do think that going through the effort of writing something down and not just typing something, but like writing something with your hand, takes that information and you're sort of using multiple parts of your brain there, which is going to make your understanding and your memory of it stronger. All right. So I would write some things down. Maybe you hear me say something out loud that you think is worth writing. Okay. So in terms of the scale of the universe, just talking about like a size scale, right? When we talk about things that are on the order of magnitude of 10 to the -15 meters across, we're talking about the size of a single proton, right? About 100,000 times bigger than that is the size of an entire atom. Right? So although every atom's got a proton, the proton takes up a very small amount of volume of that atom. And then just sort of going up this chart from left to right, you can sort of see how, although the numbers, like the exponents, don't change all that much, the scale at which that number represents is dramatically different than what's next to it. Right? So like, just look how close, like the size of a human compared to the diameter of the Earth. Right? That's like a proton sitting on the surface of a virus. Right, so a proton, and you can't see a virus with your eyes. So like, you just think about how much smaller that makes a proton. And then all the way up the other direction, right, is distance to nearby stars, diameter of our galaxy or a galaxy, and then the size of our observable universe, which is different than the entire universe, which is crazy. All right, so I'm going to pull up very quickly. I'm going to share this website with you guys. We're just going to sort of putz around with this together. This is a great website. I really enjoy going through this. I'm going to turn the music on for it in a second, so tell me if it's too loud. It's like weird, like ominous music. I'm just gonna leave it on. All right. Okay, hold on. It's doing something weird. Let me just reset this. Hold on. Sorry, that was bothering me. Oh Jesus, is that my phone? What the hell is that? It's got like a loud ding sound in my ear. Okay. Ah, there we go. That's the music. A little bit more normal now. Okay. So here we're looking at a human, some other objects that are on the same sort of scale of size. If you look at the bottom here, where my mouse is, it says 10 to the 0th power, which is just 1. Anything raised to the 0 is equal to 1. So we're talking about things that are about a meter in size. And let's get really small, right? We're gonna zoom in, and every time we pass one of these circles, it'll tell you about how much smaller we've gotten. So 10 to the -1, now we're at 10 to the -2. This is 100th of a meter, so the size of a, hold on. That's really loud. Is that too loud, folks? Could you hear me while I was narrating that? All right, sorry. I'll just not have the music on. So now we're at 10 to the -2. We're looking at things on the size of a coffee bean, an ant, a grain of rice. All right, now we are at 10 to the -3. This is a millimeter. So we're talking about the thickness of hair, a sheet of paper, the size of a pixel on your computer screen. All right, then a human egg, skin cells, right? We're now at a 10,000th of a meter. All right, silk fibers, mist droplets, cells, nuclei, X and Y chromosomes, E. coli, violet light, the world's largest virus, the size of HIV, transistor gate, right, DNA, right? And if you look, whoa, that was way too fast. Hold on. Right, we have X-rays, glucose molecules, are we're at the size of a nanometer now. So we're looking at like water molecules and carbon atoms, the smallest thing visible to an electron microscope. Right, hydrogen atoms and helium atoms, right, the smallest atoms, gamma ray wavelengths. Right now we're in picometers, 10 to the -12, femtometers, or hundreds of femtometers. We're talking about the size of a nucleus, size of an electron, size of a proton or neutron. Let's keep going. All right, we're getting to the point that lengths shorter than this are not even confirmed. Right? But we can just, scroll through and we see we got these things called quarks. Not too worried about what those are yet. Zeptometers, they really got a name for everything. Neutrinos. And every single one of these circles is 100 times, excuse me, 10 times smaller than the circle before it. So we're looking at very, very small things, right? And at the most small scale, 10 to the negative 35th meters across, we're talking about like what some physicists would call the most fundamental structure in the universe, which are strings or quantum foam. All right, we're gonna zoom out now, back to the 1 meter scale. And now we're gonna go in the other direction. All right, and every time that we see a circle, at this point, we're talking about 1,000 times larger than a person. So we're at 10, this is now 100 times bigger. Excuse me, 100 times bigger. This is now outside here, we're at 1,000 times bigger than a person. So the Washington Monument, the Hoover Dam, the Burj Khalifa, Vatican City, Central Park. We have some small asteroids and moons and comets. We have Mount Everest, the length of a New York City marathon. The size of a neutron star is smaller than a marathon. Right? Neutron stars are very small. We got some states up here. Right, this is now 1 million times bigger than a person. We have West Virginia, we have California, Italy. We got some small asteroids. There's Pluto on the right. Right, Pluto's not much bigger than, it's actually smaller than the width of the United States. There's Earth on the left, and Mars, and Venus, and Asia. All right, now we're looking at some small stars, Sirius B being among them. Somebody thought it would be funny to put Minecraft World on here. We've got Jupiter, the gas giants. Right, notice now we're at 1 gigameter, 1 million times bigger. Excuse me, 1 billion times bigger than a person. We're talking about the diameter of the sun. Stars, notice the color of the stars. You might recognize the names of some of these stars, like Polaris or Aldebaran or Rigel. Maybe you recognize Antares. Right, we're in the zone of red giant stars right now. Right, we have the Kuiper belts. Now we're starting to get into the size of nebulas. We have a light day, the distance light travels in a single day. Right, we're looking at more nebulas. All right, we are now a quadrillion times bigger than the size of a person. There's a light year, more nebulas. All right, we've got all of these nebulas, all of very different size scales too. I mean, these are thousands to millions to billions of times different in terms of the vastness of their size. All right, then you start to get into galaxies, right? Individual galaxies. You have small galaxies, larger galaxies like our Milky Way or Andromeda, even bigger galaxies. Right? Then you get into groups of galaxies, right, called clusters. Right? And there are clusters of clusters. Right, we got superclusters. And then there's the observable universe. And so we're, I know that there's no substitute for actually experiencing it, which is impossible, but hopefully this gives you some type of insight, right, into just how big our universe is and how tiny our universe can seem. Okay, so let me go back to the PowerPoint for a moment. I'm going to try to wrap things up pretty quickly now. All right, so when we talk about the about scale, right, size scale. Oh, where is it? There it is. when we talk about distances, right, it helps to talk about things in distances that make sense, right? So if we're talking about the distance from your home to LaGuardia Community College, you're probably not going to talk about that distance in terms of feet. You're not going to say, I live, 12,000 feet from LaGuardia Community College. You might say, I live 2 miles from LaGuardia Community College, right? You might say how many kilometers you live from LaGuardia Community College, but you're not going to talk about how many inches you are away, right? So when we talk about certain physical quantities, we want to make sure that the units that we choose to express those magnitudes are appropriate, right? So that they're not too confusing. And so as we start our exploration, right, in astronomy, we're going to focus mostly right now on what's in our solar system. We're going to start small, so to speak. And in doing that, I'm introducing to you here a unit of length called an astronomical unit, which is the average distance from the center of the Earth to the center of the sun. Right? We have to, it doesn't say the word average, but it says the mean distance. Mean is another word for average. We have to use the word mean distance. We can't just say the distance, because the distance between the Earth and sun changes throughout the year. Right? There are times when the Earth and sun are closer together, and there are times where they're farther apart. So we have to pick a number that doesn't change, and that would be the average. And then we can talk about the distance of objects in terms of astronomical units, right? Once we define what the unit is, now we can actually use it to measure craft, all right? And that being said, we can always convert from one unit to another. You can express a distance in meters just as much as you could express it in kilometers, just as much as you could express it in miles, inches, feet, so on and so forth. And so we're going to talk about how to do unit conversions. For some of you, that might be something you're already very comfortable with. For others of you, it might not be, and that's fine, right? My goal is to get you there. Let me see here. What do I have next? Okay, I'm going to skip this for a second. All right, I'm going to introduce one other thing, and then we're going to pause for today. Actually, yeah, no, I'm going to do one more thing, and then we'll pause. Take a look here. All right, so another unit that we use to measure distances is a light year. Now, I think for a lot of people, unless they're being taught explicitly, they might hear a light year and think that you're talking about time because you say the word year, right? But we also have other units of distance, like a light day, a light minute, a light hour, a light second, right? And essentially, it means how much light travels in that amount of time, right? In space. How far does light travel from one point to another in that amount of time, right? So a light year is a measure of distance. And it's based on the speed of light. Now, this is an approximation, okay? The speed of light's a little bit smaller than this number. It's like 2.98 times 10 to the 8 meters per second, but for all intents and purposes, we are going to just round it to 3 times 10 to the 8. All right, now that's a 3 with 8 zeros after it. Right? In other words, 300 million meters per second. That is the speed of light in a vacuum. And when I say a vacuum, I mean space. Space is essentially a vacuum. 300 million meters per second. That means that light travels the distance of 3 million football fields approximately every second. 3 million football fields per second, right? You try moving that fast, your skin will fly off you. Right, but this unit of measurement is useful when we're talking about the distance between bigger objects, right? So like from our sun to the next nearest star in the entire universe, it's 4 light years away. All right, 4 light years sounds like a nice small number, but a light year is a huge measure of distance, right? So like this is not something that we'd want to measure in inches, for example. Our galaxy, the Milky Way, is about 100,000 light years across. That means if you were standing at one edge of the Milky Way and you took a flashlight and you shined that light through the center of the Milky Way towards the other side, it wouldn't get there for another 100,000 years, because that's how long it takes light to travel 100,000 light years, right? It's like the question, you know, if you're traveling 60 miles per hour, how long does it take for you to go 60 miles? 1 hour. You're going 60 miles per hour. So it would take you 1 hour to go 60 miles, right? And like I said, right, distances could be in light hours, minutes, or even light seconds. Okay, so with the last 5 minutes before I set you all free for the day, I want to introduce to you the speed equation. Right? Might be something that you've already learned. If it is, fantastic. If not, the speed equation is incredibly important. It's one of the most fundamental basic equations that we use to describe the world around us and how objects change position with time. Right, so we have V. V stands for speed and or velocity. There is a difference between speed and velocity. I'm not super concerned with you knowing that difference right now. But we have V equals, and then we have D over T, where D could be distance or displacement. Again, not too worried about you knowing the exact difference between those two words, over time. And so essentially we're saying that speed is the rate at which distance changes, right? It is some unit of length divided by some unit of time. So meters per second is a unit of measurement of speed. Miles per hour, kilometers per hour, centimeters per year. These are all speeds, right? It's a distance over a time, right? So like to say that the continents, the Earth's tectonic plates move at a rate of about 10 centimeters per year, or you know, whatever it is, 1 centimeter per year, 10 centimeters per year, right? That's a speed. So I want to go back to the slide I had up a moment ago with the speed of light. Oh, not this. That'll be for later. All right, so the speed of light. Oh wait, did I skip it? Sorry, I'm all over the place. Here we go, speed of light. And let's say that we want to know how many meters is a light year? How many meters is a light year? I'm going to switch my screens now to my iPad, and I'm going to finish up over there so that you can see my work as I do this problem. Let me know if can you guys see it? Nope, it just went dark again. How about now? White screen? Okay. So we have that the speed of light is 3 times 10 to the 8 meters per second. Okay. This is essentially our value for, like, we can just call this V, right? In this context, C and V are interchangeable. Now, I know that that's probably going to confuse the heck out of some people, okay? And that's fine. So let me just quickly explain here. V stands for the speed of anything, right? V could be the speed of you, could be the speed of me, could be the speed of a nearby star. C is a very specific speed. C is the speed of light. And so you could take the V equals D over T equation and replace V with C, and this works, right? This is how we're going to measure the distance traveled by light in a time period of 1 year. So let me write that question out. How far does light travel in 1 year? And we want to measure it in meters. Okay. So a couple of things, two things. One, we're going to take this equation that I have written up here, and we're going to rearrange the equation to isolate distance, because that's what we're trying to solve for, right? To isolate a variable just means to get it by itself. And on this right side of the equation, we have D divided by T. We want to get rid of time, so we have to multiply it so that it cancels out like this. Right? We multiply time on both sides and it cancels. And that's how you get D equal to C times T. So this is going to be the equation that we use to solve for how far light travels. And you're going to find that there are some homework problems that require you to use the speed equation. Right? Now, when we go ahead and we try to use the equation, there's one other issue that we have. The units that we are using to measure C are meters per second. So the time that we use also has to be in seconds. Because when we multiply meters per second times seconds, then the seconds in the numerator cancels with the seconds in the denominator, and we're left in meters, which is the unit for distance. Right, so here, let me just show you really quickly. You know, distance we want to be measured in meters. The speed of light is measured in meters per second. If time is measured in seconds, those cancel out and we get a number in meters. But if we plug in a time that's measured in years, then it doesn't cancel. And that's going to be a problem. So we want it to cancel. So the first thing that we're going to do is convert time. We're going to convert 1 year. First, convert 1 year into seconds. All right. I'm not going to spend a lot of time right now talking about unit conversions because we don't have too much time. So if you want to look up how to do it, if you're really stuck, just let me know and I can find a short video for you to watch, or maybe you just go ahead and find one yourself on YouTube. But I'm going to walk you through it. We're going to take 1 year and just write it out like this. We're just going to write 1 year, and we're going to multiply it by a fraction. The fraction is going to have two numbers in it, a number in the numerator and a number in the denominator. And the units of the denominator are going to be in years. The numerator, or the idea right now is we're going to get from years into seconds. Now, the problem is a lot of us probably don't know how many seconds are in a year. That's fine. But everybody should know how many days are in a year. Right? We got about 365. It's actually a little bit more than that. It's 365.25. Think about that. Every 4 years, we have a leap year. We add a day because every 4 years, right, those 0.25s add up to 1. Boom. So we're going to take 1 year and multiply it by this fraction, 365.25 days over 1 year. The numerator and the denominator represent the same exact amount of time, right? So overall, this fraction, this parentheses thing that I just included has a value of 1 because we're taking a certain amount of time and dividing it by the same amount of time. Then we're going to multiply by another conversion factor, but this time we're going to get out of days and into hours, because that's a unit that's a conversion that we know. 1 day is 24 hours. Now days cancels. And we can just keep doing this, and we can get from hours to minutes. 1 hour is 60 minutes. Boom, now hours cancels. Then we do it again. Minutes to seconds. 1 minute, 60 seconds. Boom, now minutes cancels. Congratulations, folks. You just converted years into seconds. Now all we got to do is multiply the numbers across. So we have 1 times 365.25 times 24 times 60 times 60 divided by 1, divided by 1, divided by 1, divided by 1. And that comes out to 31,557,600 seconds. Now, we're going to use the speed equation that we wrote, or the rearranged speed equation. The speed of light is 3 times 10 to the 8 meters per second, and we're going to multiply that by a time, right? Remember, it's like saying, if you're going 60 miles per hour for 1 hour, you've traveled 60 miles. You're multiplying your speed and the time together to get the distance traveled. If you go 60 miles per hour for 2 hours, you've gone 120 miles. All right, so we're doing speed times time gives you a distance. 31,557,600 seconds. The seconds in the denominator over here cancel with the seconds in the numerator over there. And meters is the only thing left over. And so now we multiply all this through. And it comes out to 9.467 times 10 to the 15 meters. Or let's see if I still have it up here. Oh no, I don't have it up here. This is equivalent to 1 light year. All right, and you can go online, you can go onto Google and do the unit converter, and you could say how many meters is 1 light year, and it will give you this number. All right, but I just wanted to show you how you would calculate that on your own, because it's an important thing to be able to do. All right, so folks, we are at the end of what I wanted to talk about for our live session just now. So 2 things. One, for those of you that did not get here, that did not get here at 3:45, I hope that now that we know where the link is and maybe we've read through the syllabus, that we know what time we need to be here. But also, when you log onto Zoom, make sure, please, it's very important that we do this going forward, that you just change your name on Zoom to include your pronouns. All right, so if you see on my name, I have he, him, his. I see Deanna has she, her. Alexa has she, her. Sani, I see Zach has he, him, his. Right, and if you are he, him, his, she, her, hers, they, them, theirs, we all need to know so that we can address each other respectfully. And that means that everybody is doing it, right? This is whether you identify as binary or not. All right, so please make sure going forward that you do that when you log into Zoom. I will remind you. And with that, you are free to go. If anybody has any questions, I will be sticking around for another couple of minutes to address any concerns or questions that you guys have. And with that, have a great rest of the day. All right, and this lecture will be posted shortly after class ends. All right, Barrier, what's going
sorry.
on?
No, sorry. It's about the lecture video posting. Where will it be posted? Is it on Blackboard or?
So first I'm going to upload the video to YouTube, and then I'm going to embed it into our Blackboard page.
Oh, okay, got it. Thank you.
Okay, you're welcome. So it might take me a second because this is the first time I'm doing that. But that's the story. All right. Zach with the plug in the chat. Zach's got an opportunity for an artist in the room. Okay. Are there any questions that you guys have about anything in this class, anything astronomy related that you'd like to ask? If not, you can head out and have a nice day. Tiffany. I will work with you as much as you need me to make you feel really good about this math. And I promise you, we're not going to do math that's much harder than this. All right, this is just making sure that we know some of the most basic stuff that we need to know, and that's it. Right. Thank you, everybody that's saying goodbye in the chat. Thank you. Have a good day.
Professor, one more thing. The homework as of now, would it be just a discussion and?
It is just a discussion. So for some reason, when I was looking on Blackboard, even though I put a due date on the homework assignments, I didn't see it show up on the homepage. You know what I'm talking about? Like where it says what's due this week, what's due next week, what's due today, what's due tomorrow.
Okay, yeah.
Right.
I didn't see that there.
When you look there, you see the discussions, right?
Yes, I see the discussion.
Okay, so the homework, the first homework, I believe I have set to be due. Excuse me. The first homework.
Okay, so the only discussion that I see as of now is to introduce ourselves.
Sorry, yes, that's discussion 1. Each discussion, excuse me, I misspoke when I said that you should see all of them. They will pop up weekly on Mondays, and they will be due on Sunday night of that week. All right, so this week's discussion is due on Sunday the 14th. Did I just do math correctly? Sunday the 14th.
Yes. 14th, yes.
Yes. Okay. But the first homework, if you click on the homework and labs tab, and you click on first problem set, I'll make an announcement. The first homework is due on March 21st. That's a Sunday night at 11:59 p.m. All right, so you've got 2 weeks to do the first homework assignment. In fact, you could just go ahead and do all of the homeworks right now. You could do all the homeworks and all the labs.
I tried to click. Oh, sorry to cut you off. Continue.
No, please tell me if there are any issues. I want to know.
No, so I tried clicking on the homework link and it says course link is not established yet.
Course link is not established yet.
Right.
Okay, I will look into that and figure out why that's happening, and then I will get back to you.
Okay, thank you so much.
All right, thank you for letting me know. All right, same thing, Chris. Okay. Yeah, let me figure out what's going on here. All right, any other questions? Jasmine, Angelique, Carlos, was there anything that you wanted to address?
Not currently, but
Just hanging
if
out?
anything. Yeah.
Okay, no
Yeah.
problem. No problem, Jasmine. All right, I need to figure out why that's not working. Can you do me a favor and just screenshot what you're getting on your screen when you click on it? And can you
Oh,
email
yes,
that to me,
yeah.
please?
Okay, no problem.
Thank you very
I
much,
could, I
Barry.
could share my screen if you like.
Sure.
Uh,
Hold on, let me
you-
stop the recording so that at least that's out of the way.
Okay.